Magma is the key to the Moon's makeup. For more than a century, scientists have squabbled over how Earth's moon formed. But researchers at Yale and in Japan say they may have the answer. Many theorists believe a Mars-sized object slammed into the early Earth, and material dislodged from that collision formed the basis of the Moon. When this idea was tested in computer simulations, it turned out that the Moon would be made primarily from the impacting object. Yet the opposite is true. We know from analyzing rocks brought back from Apollo missions that the Moon consists mainly of material from Earth. A new study published April 29 in Nature Geoscience, co-authored by Yale geophysicist Shunichiro Kurato, offers an explanation. The key, Kurato says, is that the early proto-Earth, about 50 million years after the formation of the Sun, was covered by a sea of hot magma, while the impacting object was likely made of solid material. Kurato and his collaborators set out to test a new model based on the collision of a proto-Earth covered with an ocean of magma and a solid impacting object. The model showed that after the collision, the magma is heated much more than solids from the impacting object. The magma then expands in volume and goes into orbit to form the Moon, the researchers say. This explains why there is much more Earth material in the Moon's makeup. Previous models did not account for the different degree of heating between the proto-Earth silicate and the impactor. In our model, about 80% of the Moon is made of proto-Earth materials, said Kurato, who has conducted extensive research on the chemical properties of proto-Earth magma. In most of the previous models, about 80% of the Moon is made of the impactor. This is a big difference. Kurato said the new model confirms previous theories about how the Moon formed, without the need to propose unconventional collision conditions, something theorists have had to do until now. For the study, Kurato led the research into the compression of molten silicate. A group from the Tokyo Institute of Technology and the Riken Center for Computational Science developed a computational model to predict how material from the collision became the Moon. The first author of the study is Natsuki Hosono of Riken. Additional co-authors are Junichiro Makino and Takayuki Saito. NASA's InSight detects first likely quake on Mars. NASA's Mars InSight lander has measured and recorded for the first time ever a likely Marsquake. The faint seismic signal, detected by the lander's Seismic Experiment for Interior Structure (SEAS) instrument, was recorded on April 6, the lander's 128th Martian day, or SOL. This is the first recorded trembling that appears to have come from inside the planet, as opposed to being caused by forces above the surface, such as wind. Scientists still are examining the data to determine the exact cause of the signal. InSight's first readings carry on the science that began with NASA's Apollo missions, said InSight principal investigator Bruce Bannert of NASA's Jet Propulsion Laboratory (JPL) in Pasadena, California. We've been collecting background noise up until now, but this first event officially kicks off a new field, Martian seismology. The new seismic event was too small to provide solid data on the Martian interior, which is one of InSight's main objectives. The Martian surface is extremely quiet, allowing SEAS, InSight's specially designed seismometer, to pick up faint rumbles. In contrast, Earth's surface is quivering constantly from seismic noise created by oceans and weather. An event of this size in Southern California would be lost among dozens of tiny crackles that occur every day. The Martian Sol 128 event is exciting because its size and longer duration fit the profile of moonquakes detected on the lunar surface during the Apollo missions, said Lori Glaze, Planetary Science Division Director at NASA headquarters. NASA's Apollo astronauts installed 5 seismometers that measured thousands of quakes while operating on the Moon between 1969 and 1977, revealing seismic activity on the Moon. Different materials can change the speed of seismic waves or reflect them, allowing scientists to use these waves to learn about the interior of the Moon and model its formation. NASA currently is planning to return astronauts to the Moon by 2024, laying the foundation that will eventually enable human exploration of Mars. InSight's seismometer, which the lander placed on the planet's surface on December 19, 2018, will enable scientists to gather similar data about Mars. By studying the deep interior of Mars, they hope to learn how other rocky worlds, including Earth and the Moon, formed. 3 other seismic signals occurred on March 14, Sol 105, April 10, Sol 132, and April 11, Sol 133. Detected by SEAS more sensitive very broadband sensors, these signals were even smaller than the Sol 128 event and more ambiguous in origin. The team will continue to study these events to try to determine their cause. Regardless of its cause, the Sol 128 signal is an exciting milestone for the team. "We've been waiting months for a signal like this," said Philippe Lognanet, SEAS team lead at the Institut de Physique du Globe de Paris (IPGP) in France. "It's so exciting to finally have proof that Mars is still seismically active. We're looking forward to sharing detailed results once we've had a chance to analyze them." Most people are familiar with quakes on Earth, which occur on faults created by the motion of tectonic plates. Mars and the Moon do not have tectonic plates, but they still experience quakes, in their cases, caused by a continual process of cooling and contraction that creates stress. This stress builds over time, until it is strong enough to break the crust, causing a quake. Detecting these tiny quakes required a huge feat of engineering. On Earth, high-quality seismometers often are sealed in underground vaults to isolate them from changes in temperature and weather. InSight's instrument has several ingenious insulating barriers, including a cover built by JPL called the Wind and Thermal Shield, to protect it from the planet's extreme temperature changes and high winds. SEAS has surpassed the team's expectations in terms of its sensitivity. The instrument was provided for InSight by the French space agency, Centre National d'Études Spatiales (CNES), while these first seismic events were identified by InSight's Marsquake service team, led by the Swiss Federal Institute of Technology. "We are delighted about this first achievement and are eager to make many similar measurements with SEAS in the years to come," said Charles Yana, SEAS Mission Operations Manager at CNES. JPL manages InSight for NASA's Science Mission Directorate. InSight is part of NASA's Discovery Program, managed by the agency's Marshall Space Flight Center in Huntsville, Alabama. Lockheed Martin Space in Denver built the InSight spacecraft, including its cruise stage and lander, and supports spacecraft operations for the mission. A number of European partners, including CNES and the German Aerospace Center (DLR), support the InSight mission. CNES provided the SEAS instrument to NASA, with the principal investigator at IPGP. Significant contributions for SEAS came from IPGP, the Max Planck Institute for Solar System Research in Germany, the Swiss Federal Institute of Technology (ETH Zurich) in Switzerland, Imperial College London and Oxford University in the United Kingdom, and JPL. DLR provided the Heat Flow and Physical Properties Package (HP3) instrument, with significant contributions from the Space Research Center of the Polish Academy of Sciences and Astronica in Poland. Spain's Centro de Astrobiología supplied the temperature and wind sensors.